My name is Vamshi Prasad. Last week we have discussed about the types of polarization related to the electronic polarization and orientation polarization. Today topic is types of polarization and internal field or local field or Lorentz field. Okay. My name is Vamshi Prasad. I am working in PVRT Narsapur campus, physics department, in the basic sciences and humanities. Today we will discuss about the types of polarization and internal field of a dielectric material. Now you can see here what is the importance of ionic polarization in dielectric material. In the previous class we discussed about the electric polarization and orientation polarization. In ionic polarization is mainly due to the displacement of the cation and anion in opposite directions and occurs in ionic solid. Ionic polarization is denoted by, we are taking the equation is mu is equal to alpha E. That means induced dipole momentum is increases, the strength of the electric field is also increases. Here alpha is said to be polarizability. I am writing here alpha suffix I, it is said to be ionic polarizability. So ionic polarizability can be written as alpha I is equal to mu divided by E. That means ionic polarizability is defined as the induced dipole moment per unit electric field. So I am taking here cation and anion in opposite direction occurs in ionic solid. Now I am taking about the NaCl is the one example for the ionic polarization. In this NaCl, I am taking about the Na plus and Cl minus. That means equal magnitudes. Two separate charges are separated by some amount of distance d. It is said to be dipole moment. So I am taking here NaCl, that is the molecule. I am applying about the external electric field in the positive x direction. Let an electric field is applied in the positive direction. Here what happens means the positive ions move by some left hand side direction x1 and negative ions move by some direction x2. Here I am considering about the capital M is the mass of the positive ion and small m is the mass of the negative ion. In that manner, I am taking about the x1 is the displacement of the positive ion and x2 is the displacement of negative ion. According to the in simple harmonic motion, the total displacement is directly proportional to the, that means the amplitude of the system is directly proportional to the displacement of the particle, that is y equal to kx. Here kx is some constant, x is the displacement of the particle. In that manner, the total displacement can be written as x is equal to x1 plus x2. What is x1 here? x1 is the positive ions move by some direction x1. What is x2 here? x2 is the negative ions move by one more direction. So total displacement can be written as x equal to x1 plus x2. I am taking equation number 1. So our phenomena is to calculate about the ionic polarizability of the NaCl molecule. So due to the induced dipole moment, the ionic polarization is given by mu is equal to E into x. E is the charge. So x is the total displacement. The total displacement can be written as x1 plus x2. According to the restoring force constant, in our intermediate level we have seen this equation. The restoring force constant is directly proportional to the x is the displacement of the particle. Here k is the constant and x is the displacement of the particle. But what is our x here? X is the displacement. So based on this equation, I am taking the restoring force constant on positive and negative ions is written as F is equal to K1 into X1 and F is equal to K2 into X2, right? So that X1 can be written as F by K1 and X2 can be written as F by K2. What is here F here? F is the total force acting on the system. F is the force, right? So according to this equation, I am defining about the displacement of the positive ion x1 and x2 is the displacement of the negative ion x2. So x1 is equal to F by K1 and x2 is equal to F by K2. Coming to the next slide, you can see the diagram here, ionic polarization. See here, I am taking about the dipole. One positive charge and one negative charge separated by some amount of distance, it is said to be dipole. So in the absence of external electric field, you can see here, positive and negative ions are placed in one particular direction. Now, in the presence of the external electric field, the positive ions move to the right side direction x1 and negative ions move to the left hand side direction x2. Now, you can see here, negative ion with respect to the x2, positive ion with respect to the x1. I am writing here this total displacement x is equal to x1 plus x2, right? Now you can see here, with respect to the external electric field, cation that is x1, anion that is x2. Now you can see here, one is the positive side end, another one is the negative side end. So here, when an electric field is applied to the molecule, our molecule is NaCl, the positive ions displaced by x1 to the negative side electric field and negative ions displaced by x2 to the positive side of the field. Now you can see anion, negative side, cation, positive side. We are applying here electric field. When electric field is applied to the molecule, the positive ions displaced by x1 to the negative side of electric field and negative ions displaced by x2 to positive side of the field, right? So here, according to the restoring force constant, here K1 and K2 are the constant parameter. The constant parameter called as namely restoring force constant. Now we can see here, restoring force constant can be written as F is equal to small e into capital E. Small e is the charge, capital E is the electric field intensity. Based on this equation, restoring force constant depends upon the mass of cation and mass of ion. So F is the applied field here. According to the equation number 1, x1 is equal to F by capital M into omega naught square. What is capital F value? Capital F value can be written as small e into capital E. What is capital M here? Capital M is the mass. Okay, capital M is the mass of the ion, right? Same like another displacement of the ion x2 is equal to capital F divided by small m into omega naught square. Omega naught square is the important parameter. That important parameter name it is called about the natural angular velocity of the ion. Apply F is equal to small e into capital E. This is for x2 for small m omega naught square. x1 is equal to capital M omega naught square, right? According to the equilibrium condition, Lorentz force and restoring force constants are equal and opposite. Therefore, induced dipole moment can be defined as mu is equal to small e into x. What is our x? Total displacement, right? So x can be written as x1 plus x2. Substitute here x1 value, that is small e into small e divided by capital M into omega naught square, and also substitute the x2 value small e into capital E divided by small m omega naught square, right? Now take common factor, charge into external electric field divided by omega naught square. Take this one is the common, 1 by capital M plus 1 by small e. This is for the equation number 5, right? Coming to the next slide, from the definition of dipole moment, charge induced dipole momentum mu is equal to charge into distance of separation, right? What is our distance? Now again x is the distance, right? So induced dipole momentum mu is equal to small e into capital X. Substitute the x value here. In previous case, equation number 5, right? Substitute this value here. We will get about the final equation for equation number 6. Capital 1 by capital M plus 1 by small m. Omega naught square is the natural frequency. We can write angular velocity of the ion. According to our concept, induced dipole momentum can be written as alpha into capital E. Alpha, it is said to be polarizability. The polarizability can be defined as the induced dipole moment per unit electric field. So here, induced dipole momentum is increases the strength of the external electric field is also increases. So we have to find out for ionic polarizability, right? So ionic polarizability is equal to, substitute the induced dipole moment and value here. You can see here E square into capital E divided by 1 by omega naught square into, this is about the reduced mass of the system, this equation. Substitute here, we will get this equation. Capital in this equation, capital E gets cancelled. We will get the final equation. Ionic polarizability is equal to 1 by capital M plus 1 by small m. This equation, okay, this is the reduced mass of the system. Okay. Now, according to ionic polarization, ionic polarizability, that is alpha, is inversely proportional to the square of the natural frequency of the ionic molecule. This is about the our natural frequency of the molecule, omega naught square, right? And its reduced mass. What is our reduced mass? Reduced mass is equal to 1 by capital M plus 1 by small m. So this is about the required expression for the ionic polarization of the NaCl molecule. In that one, we can see here, this polarization occurs at frequency nearly 10 power 13 Hz rate. That means it represents about the infrared frequency. It is a slower process compared to the electronic polarization. So ionic polarization is, it is independent of temperature. It is main point is, it is independent of temperature. So coming to the next slide, one more polarization is space charge polarization. Compared to the electronic polarization, space charge polarization and orientation polarization, space charge polarization is the having the about the least parameter. That means the space charge polarization is very small compared to the other types of polarization. So that space charge polarization can be eliminated. So here what is the importance of space charge polarization is, space charge polarization occurs due to the accumulation of charges at the electrons or at the interfaces in a multi-phase material. In this diagram, we are seeing a negative sign, positive, negative with positive, positive, negative, positive and negative. In the absence of external electric field, what is about this space charge polarization? Now, if you apply about the, in the presence of external electric field, all negative signs, negative charges will come one side direction and positive charges will come into the one more direction, like that. This is said to be space charge polarization. In the crystalline material, we can see about the all the atoms or molecules are arranged in a periodic arrangement. In this manner, the space charge polarization can be very small compared to the other types of polarization. So the space charge polarization we are eliminated. That means we are not considering about the total polarization process. So that the ions diffuse over appreciable distances in response to the applied field, giving rise to the redistribution of charges in the dielectric material. We are taking about the dielectric material in the space charge polarization. Now you can see here, according to the total polarization is related to the sum of the contribution of the various sources. So total polarization can be written as ionic polarization plus electric polarization plus orientation polarization plus space charge polarization. So here, since space charge polarizability is very small compared to the other types of polarizabilities, then total polarizability of a gas can be written as alpha. Alpha it is said to be polarizability. The total polarizability can be written as alpha E, that is electronic polarizability plus ionic polarizability plus orientation polarizability. Now, in the previous classes, we derived about the electronic polarizability, orientation polarizability. Now you can see, now just half an hour back, just 1 minute back, we have derived about the ionic polarizability equation. Now you can see here, substitute about the polarizability terms in this equation. Alpha is equal to 4 pi epsilon naught into r cube plus ionic polarizability equation this one, orientation polarizability value this one. In this manner, our aim is to find out for total polarization of the system. So according to the polarization vector, P is equal to small n into capital mu. Capital N is the number of dipoles per unit volume of the material. So that induced dipole momentum mu is equal to alpha into E. It is said to be dipole moment. In this equation, total polarization P is equal to N into what is mu value here? Alpha E. Substitute in this equation. P equal to N alpha into E. What is our alpha value? We can see here. This is about the alpha value. Take P equal to Ne as common. Substitute about the electronic polarizability E value and ionic polarizability value plus orientation polarizability value. Space charge polarization is very small, so we are not counting about the space charge polarization. This equation represents about the total polarization of the system. That's why it is said to be Langevin-Debye equation. Okay, this is the important aspect for the dielectric material. Okay, now coming to the next slide, one more topic is internal fields or local fields or Lorentz field. This is about the important topic for the dielectric material. The main the main aim of internal field of dielectric material is we have to find out for the total electric field is equal to the sum of the electric field. That means we are taking about the parallel plate capacitor. We are keeping about the one spherical cavity inside the material. Okay. So here, what is the aim of the local field is? Local field or internal field in dielectric material is the space and time average of the electric field intensity acting on a particular molecule in the dielectric material. In the dielectric material, we are keeping about the one spherical region of the molecule. How to find out about the internal field related to dielectric material is we have to find out about the external electric field. EI is equal to, that means internal electric field is equal to E1 plus E2 plus E3 plus E4. That means we have to apply external electric field to the dielectric material along the x direction, along the opposite direction, along the vertical direction and along the spherical cavity of the material. In this internal field, we are taking about the dielectric be placed between the plates of a parallel plate capacitor. Why you are choosing about the parallel plate capacitor means the capacitor is the energy storage device. It is about the in the parallel plate capacitor, one end is positive plate taking place, another end is the negative plate taking place. Once if you apply the external electric field, induced charges will takes place. So in the parallel plate capacitor, we are keeping about the one spherical region. That means we are keeping about the molecule. So here we are taking out the parallel plate capacitor. Let there be imaginary spherical cavity around the atom. We are defining about the notation as capital A inside the dielectric metal. Here the internal field at the atom site capital A can be made up of four components. Just like we have seen, right? EI is equal to E1 plus E2 plus E3 plus E4. First we have to define about the internal electric field is equal to E1 comma E2 comma E3 and E4. What is the E1, E2, E3 and E4? How we can define is consider. This is about the diagram. Dielectric material, we are taking about the parallel plate capacitor. Now we are keeping about the molecule here. This is said to be spherical cavity, that is a sphere. Now we are applying the external electric field in this direction. Okay, see a positive plate with negative plate. If you apply the external electric field, charges are accumulated with each other. Okay, see here. Internal field is the total electric field at the atomic side. Consider a dielectric material is placed between the parallel plate capacitor. This is said to be parallel plate capacitor. In this parallel plate capacitor, let there be imaginary spherical cavity around the atom A. You can see the diagram inside the dielectric material. It is assumed that the radius of the cavity is very large compared to the radius of the atom. This is about the main point for the cavity. One more time, I am repeating the word. it is assumed that the radius of the cavity is very large compared to the radius of the atom. So we have to find out for what is the radius of the atom with respect to the charge dq on the element. So the internal field at the atom side can be made up of the following four components: E1, comma E2, comma E3 and E4. Coming to the next slide, you can see about the diagram. See, this is said to be spherical cavity, parallel plate capacitor. One end is positive charge, another end is negative charge. This is said to be spherical cavity. This is the dielectric material. Okay. See here, if you apply we are applying about the external electric field. The charges are accumulated with each other. Positive with negative and negative with positive sign. This is said to be surface charge. You can see here. This is said to be surface charge. In the surface charge also, one end is positive direction, one end is negative. Inside it is the cavity, spherical region, spherical cavity. We are defining about the at the atom capital A. Okay. See here, in the mathematical expression point of view, I am defining about the internal field. That is, internal field is denoted by E suffix I is equal to, in the summation form, E1 plus E2 plus E3 plus E4. Now you can see the equation number 1. In this equation, what is the E1? How we can define about this 4 parameter related to the different words. See here, field E1. E1 is field intensity due to charge density on parallel plate plates. Okay, what is electric field E2? E2 is the field intensity at capital A due to charge density induced on two sides of dielectric material. That means along the one direction electric field is applied, that is E1. One more direction is E2, that is about the opposite direction, E2. Okay, field E1 and field E2. Field E2 is induced, that is charge density induced on two sides of the dielectric material. After that, field E3. E3 is field intensity at atom A due to other atoms contained in the cavity and for a cubic structure. Our element is cubic structure, that is about the spherical region, right? Field E4. E4 is field intensity due to polarization charge on surface of spherical cavity. So we have to define what is E1, what is E2, what is E3 and E4. Our aim is to calculate for local field of a dielectric material, or we can say it is the Lorentz field. Local field or Lorentz field. We are taking about the dielectric material, that is about the parallel plate capacitor. Now you can see about the mathematical derivation part. How to calculate about the field E1. What is E1? E1 is field intensity due to charge density on the parallel plate capacitor. Now this is said to be parallel plate capacitor. We are keeping about the dielectric material. If you apply the external field in this direction, now you can see positive with negative side direction. How to calculate about the field E1? See, this is about the spherical region, cavity A. In the mathematical point of view, E1 is field intensity due to charge density on the plate. In the previous class, we already discussed about equation number 1. That means electric flux density can be written as D is equal to, D is directly proportional to capital E. So, D is equal to epsilon into capital E. This is said to be permittivity. Which type of permittivity? Dielectric permittivity or dielectric constant. Based on this equation, I am defining about from the field theory, E1, field E1 is equal to D, that means electric flux density divided by epsilon naught. Epsilon naught is said to be permittivity of the free space. Okay, now you can see here in this equation, permittivity, that means dielectric constant can be defined as permittivity of the free space into relative permittivity, right? This is said to be equation number 2. In the equation 2, one more parameter is there. That parameter is said to be P. Why you are choosing P means The polarization measures the additional flux density compared to the free space of the material. Now that D, electric flux density, can be written as permittivity of free space into field E plus P. P, it is said to be polarization. Okay, so substitute equation 2 in equation 1, we get E1 is equal to, what is our D value? Epsilon E plus P divided by epsilon naught, right? So in this equation, you can simplify equation number 3, we will get about the equation number A. That means field E1 due to charge density on the plane is given by E plus P by epsilon naught. P is said to be polarization. This is the required expression for the field E1. Coming to the next slide, calculation of E2. Field E2 is field intensity at A due to charge density induced on two sides of the dielectric material. In the previous case, we are applying about the electric field in this direction. In the field E2, we are applying about the electric field opposite direction. That's why E2 is equal to minus P by epsilon naught. P, it is said to be polarization. Now you can see here, I am mentioning about the one note here. Negative sign indicates polarization on dielectric material is opposite to external field applied between the parallel plate. That's why here in this equation E2 is equal to minus P by epsilon naught. This is the required expression for the field E2. Now field E3, calculation of field E3. What is E3? E3 is field intensity at A due to other atoms contained in the cavity and for a cubic structure. In the field E3 direction, we are taking about the spherical, that is about the cubic structure. So that E3 is field, that is field intensity at A due to other atoms contained in the cavity and for a cubic structure, the total field E3 is equal to 0. Simply we can say it is the symmetric charge distribution. All the charges are cancelled with each other. Now you can see here in this diagram, because of symmetric charge distribution, E3 is equal to 0. Okay, E3 is the, because of symmetry charge distribution, total field is equal to 0. Our main aim is to calculate for field E4. Field E4 is the typical task for the dielectric material. We are seeing about the enlarged view of the spherical region. In this diagram, we are keeping about the spherical cavity, right? That is in the dielectric material, we are keeping about the one spherical region. This is said to be enlarged view of the cavity. So that E4 is field intensity due to polarization charge on the surface of spherical cavity. Now in this diagram, you can see here, we are taking about the positive charges on one side and negative charges on other side. We are calculating about the what is the spherical shell and about the what is the surface of the sphere and also about the what is the charge of the element. In this sphere, you are dividing about the number of pieces. I am taking about the one piece, that is the dq, it is said to be charge of the element. In the mathematical expression point of view, you have to take for right angle side diagram, that is sin theta, and one more right angle side diagram for cos theta. That means horizontal components are cos theta and vertical components are sin theta. We are calculating about the first, what is the surface area of the sphere. In the mathematical point of view, we can see here E4 is field intensity due to polarization charges on surface of cavity was calculated by the Lorentz in the following way. That's why it is said to be Lorentz field also. First, we have to define about the what is surface area of the sphere. So the surface area of the sphere is lying between the theta and theta plus d theta. So now I can see about the diagram. R is about the radius, right? So first you have to define about what is the surface area of the sphere. What is theta here? Theta is the direction. Here, theta is the direction with reference to the direction of the applied force. So the surface area, that is denoted by dA. Now you can see here surface area dA is equal to 2 pi into PQ into QR. In the mathematical expression point of view, we have to take for the right angle side diagram, that is PQ into QR. So what is about the PQ is, in the right hand side triangle diagram, sin theta is equal to PQ by R. Therefore PQ is equal to R sin theta, and also theta. Theta it is said to be direction, right? So d theta equal to QR by R. Now you can see here d theta is equal to Q. This is said to be one particular element, right? See here d theta equal to QR by R. So that QR is equal to R into d theta. Give some equation number 1, 2 and 3. Please here substitute equation 2 and equation 3 in equation 1. What is dA? dA is said to be surface area of the sphere, right? Hence dA is equal to 2 pi. What is PQ value? PQ is R sin theta into what is QR? QR is R d theta, right? This is the equation number 4. After that, surface area dA is equal to 2 pi R square into sin theta d theta. This is the surface area of the sphere. Give some equation number 5. After that, charge on the surface. Charge on the surface. Define about the dq, right? So charge on the surface dq is equal to P cos theta into dA. That is P cos theta is normal component. We are taking about the normal component of the area. That's why we are defining about the cos theta term. That is P cos theta into dA. Give some equation number 6. Coming to the next slide. Substitute equation 5 in equation 6. We get charge of the element dq is equal to P cos theta into dA. This is the dA equation. dA is the surface area of the sphere. So dA value is 2 pi R square into sin theta d theta. That is the equation number 7. After that, the field due to charge dq at atom A is donated by dE4 in the direction theta is equal to 0. That means we are taking about the, according to the resolution of vector concept, we are taking about the perpendicular component position. dE4 is equal to dq into 1 into cos theta divided by 4 pi epsilon naught square. That means the dE4 component is this is the dE4 component can be dE4 by taking about the horizontal component and vertical component. Some horizontal component is cos theta and vertical component is sin theta. That's why we are taking about the normal component of the area here. dE4 is equal to charge element dq into 1 into cos theta divided by 4 pi epsilon naught square. Okay. In this equation, we can write the simplified manner. dE4 is equal to dq cos theta divided by 4 pi epsilon naught into r square. That is the equation number 8. After that, substitute equation 7 in equation 8. We get dE4 is equal to, what is dq value? dq is equal to P into 2 pi r square sin theta into cos theta d theta into 1 into cos theta divided by 4 pi epsilon naught into r square. Therefore, dE4 is equal to P cos theta into 2 pi r square sin theta into d theta into cos theta divided by 4 pi epsilon naught square. Simplify this equation, we will get about the dE4 is equal to P sin theta into cos theta into d theta divided by 2 epsilon naught. Epsilon naught is said to be dielectric constant, or it is said to be permittivity of the free space. Now coming to the next slide, how to calculate about the field E4. Now we are taking about the integral, that is d integral dE4 is equal to, take p by 2 epsilon naught common, 0 to pi. Why you are choosing about the 0 to pi means we are taking about the sphere. Okay, we are taking about the half of the sphere. Okay, 0 to pi, that is 0 to 180 degrees into cos square theta sin theta d theta. Let's substitute, assume that x equal to cos theta. Now we can differentiate here, minus sin theta d theta is equal to d theta. What are the limits? Limits between lower limit is 1 and upper limit is minus 1. Substitute this limit in this equation. Integral d4 equal to, take p by 2 epsilon naught common, lower limit is 1, upper limit is minus 1. So x value is x square, sin theta value is minus dx. We can integrate this equation. In the integral formula, integral x square dx equal to, we can write x cube by 3. Lower limit is 1, upper limit is minus 1. So integral this equation, we will get the final equation as E4 is equal to P by 3 epsilon naught. Compared to the remaining three fields, field E1, field E2 and field E3, field E4 is the important derivation for the, we have to calculate for surface of the sphere and charge element. So finally E4 will get about the P by 3 epsilon naught. Now we can see about the, well, we can see about the, what is the mathematical equation for the E1, E2, E3 and E4. See here. E1 is the field intensity due to charge density on the plate. We are defining about the E1 is equal to d by epsilon naught. So electric flux density d equal to permittivity into electric field intensity plus polarization. Finally, we will get about the mathematical point of view. E1 is equal to E plus P by epsilon naught. Next one, field E2 is, E2 is the field intensity at edge due to charge density induced on two sides of the dielectric metal. Therefore, E2 is equal to minus P by epsilon naught, that is equation number B. What about E3? E3 is the field intensity at edge due to other atom contained in the cavity. It is for the cubic structure, right? So E3 is equal to 0 because of symmetry charge distribution. We have derived about the equation A, B, C and C. After that, field E4. E4 is field intensity due to polarization charge on surface of the spherical cavity. We can define about all the four parameters E1, E2, E3 and E4. Our aim is to calculate for internal field of a dielectric material or Lorentz field. So we have to define previously, right? EI is equal to internal field of dielectric material is equal to EI is equal to E1 plus E2 plus E3 plus E4. What is E1? Equation number A. What is E2? Equation number B. What is E3? Equation number 0. What is E4? P by 3 epsilon naught. Simplify this equation, we will get about the EI is equal to E plus P by 3 epsilon naught. So this is about the required expression for the internal field or Lorentz field of a dielectric material. Okay. In the next class, we can see about the Clausius-Mosotty relation based on the internal field or Lorentz field of a dielectric material. After that, what is the piezoelectricity material and what is the pyroelectricity material? How to differentiate about the piezoelectric and pyroelectric material? What are the applications of dielectric material? We can see about the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.